This video will talk about network technologies beyond 5G and how it can be implemented in smart cities. Ah yes, 5G, the cool new kid on the block. In Malaysia, as of September 2022, this fifth generation of cellular network already has a 33% rollout across the nation. This percentage is in line with the DNP's goal to cover 40% of the population by the end of 2022. And by 2024, it is expected that 80% of the populated areas will already have access to the network. So, the transition of 5G is still under its way. But did you know that the bus is already building around 6G? To understand more about the possibility of what lies beyond 5G, let's first take a look at what 5G actually is. 5G is the direct successor of 4G, the fourth generation of cellular network. Unlike its predecessor, 5G architectures are software defined, meaning that its networking functionalities are managed through software rather than hardware. This is achievable through the virtualization of RANs, or radio access networks. Virtual RANs free 5G networks of the constraints suffered by 4G, mainly in regards of its space proximity and complex infrastructures, allowing it to have a much higher speed, low latency, and a lack of need for landlines. Out of those three, high speed is the main selling point. Some expert even claims that, theoretically at least, 5G speed could eventually exceed a frequency of 10 GHz per second. But like any other tech advancement, it doesn't stop there. According to Global Service Director John Bryan, the next generation of cellular networks, aka 6G, will take 5G high throughput capabilities to a whole new level by tapping into the terahertz radio frequency band. Even more excitingly, a world beyond 5G might mean a digital world that is completely free from latency and processing delays. Much of these speculations come from the current rapid advancement in virtual and augmented realities, specifically the frenzy around the metaverse as the future of the internet. In order to support this future, beyond 5G technologies will have to be fast, efficient, and more intelligent than ever. It will utilize more advanced AIs and machine learning algorithms to support its network, which entails for the maximization of IoT to provide immersive and jaw-dropping user experiences. It is important to note that all these evolutions will inevitably cause changes in the architecture of the network layers. And while we can't know for certain how they will eventually be, we can make predictions on what we already know. Let's take a look at a few of them.
Now that you know what 5G and B5G are, let us move on to the changes beyond 5G will do to the OSI model. The first layer of discussion will be the transport layer, which is the fourth layer of the OSI model. Before we begin, what exactly is the transport layer and how does it relate to our discussion? The transport layer plays a role of providing transparent transfer of any data between end users, and it provides reliable data transfer services to the upper layers. This layer is in control of the reliability of a given link through flow control, segmentation and desegmentation, as well as error control. In this 5G era, the users are not just humans but the billions of devices that will be provisioned to specific end users, specific needs, and so on. One of the most cutting-edge features of the 5G architecture is its reliance on 5G network slicing and multiplexing. But let us dive in deeper to the topic of multiplexing and its relation to B5G. So what exactly is multiplexing? Multiplexing, or also known as muxing, is a way of sending multiple signals or streams of data over a communications network simultaneously in the form of a single, complex signal. The reasons for multiplexing are to allow network devices to communicate with one another without needing a separate connection between each device, although still needing a shared media. Besides that, it is to more effectively use pricey or limited network resources. Multiplexing, for instance, can be used to broadcast several signals across a satellite uplink or over a cable or fiber strand connecting major metropolitan areas. There are multiple types of multiplexing, but OFDM, orthogonal frequency division multiplexing, is here to stay. It is resilient to the electromagnetic interferences, and it also helps in enabling an efficient use of the total available bandwidth. Other than that, it is more resistant to any interference due to the several channels available. A university in Osaka, Japan, and a university in Australia have researchers developing a silicon-based microchip with a unique multiplex to partition data and allow for more effective handling of terahertz radiation. The device allegedly delivers data at a rate of 11 gigabits per second during their test runs, as compared to the 5G's limit of 10 gigabits per second. The future is bright with B5G. 6G is expected to be providing substantially higher throughput and data flow. It will supply several gigahertz channels at a simultaneous theoretical data throughput of roughly 11 Gbps. Deploy up to 360 MHz bandwidth channels, as well as a multiplex up to 8 spatial streams.
"5G utilization in application layer have summarized to mobile computing technology. Mobile computing is a technology that allows us to transmit data, audio, and video via devices that are not connected with any physical link. Due to the popularity of intelligent terminals and applications, the demand for mobile data services such as checking your email, streaming music or video, checking social media sites is growing. In order to speed up network access speed, we need to sync capacity, content storage, and distribution of the radio access network based on the user perception. Intelligent push demand content to enhance the user experience. Therefore, the use of content delivery wireless network technology is used to increase the radio base station computing and storage ability to form a distributed content delivery network (CDN). CDN is a group of servers which work together to provide fast delivery of internet content. MECC is a public key cryptographic algorithm that is used for both authentication and confidentiality of data, which open wireless network information in real time, personalized mobile user, and context-sensitive experience. MECC is suitable for the emerging smart applications such as augmented reality, mobile office, and smart home. In the mobile social network, popular content usually get a large number of mobile users of common concern within relative close range. At the same time, advances in technology with beyond 5G, mobile devices can provide spread capacity such as computing, storage, and context.
As amazing as the use of 5G in the physical layer currently, it is still insufficient to satisfy the requirements of latency, bandwidth, and traffic density in 2030 and beyond, where next-generation wireless communication networks with revolutionary enabling technologies is required. Hence, beyond 5G is introduced to support superior performance by providing advanced functions such as ultra-low latency, ultra-high reliability, global coverage, massive connectivity, and better intelligence and security levels, where a 10-time increase in network energy efficiency over 5G and a 100 times increase over 4G is supported. Some of the potential evolutionary technologies that beyond 5G can bring to the table includes joint sensing and communication, holographic, multiple input, multiple output surfaces and beamforming, free duplexing and spectrum sharing, massive device-to-device communication, e-health and biosensing, automated vehicles and robotic for Industry 4.0 and beyond, software-defined networking and network function virtualization. In addition, the potential of radio signaling and maximal cognitive for intelligent radio transmission can also be fully realized through AI-empowered system with the aid of machine learning algorithms. For example, beyond 5G will trigger massive data connections with private, confidential, and sensitive information. The security of wireless communications is conventionally established by cryptographic schemes and protocols, in which the secret key distribution is one of the essential primitives. Hence, channel reciprocity-based key generation (CRKG) is an emerging physical layer-based technique to establish secret keys between devices. For instances, CRKG with massive multiple input, multiple output and wave is a study conducted on how to increase the secret key rate of CRKG by leveraging the advantages of massive multiple input, multiple output and wave. The impact of number of antennas on secret key rates is analyzed and demonstrated through simulations. In massive multiple input, multiple output systems, one base station employs a large number of antennas simultaneously serving tens of user terminals in the same time frequency resource. By employing many antennas, energy can be focused into small spatial regions, providing high spatial resolution and reducing intra-cell interference. Thus, massive multiple input, multiple output can significantly improve the spectral efficiency and power efficiency. Next, wave communication corresponds to 30 to 300 GHz frequency bands, in which to support data rates of multiple gigabits per second. Compared to sub-6 GHz bands, wave bands provide large available bandwidths. Due to small wavelength wave frequencies, many antennas can be packed into a physically limited space. For instances, the number of antennas at 70 GHz can go up to 1024 at base station and 64 at the user equipment. However, without spatial coding gain, the attenuation at wave can be too large. Thereby, wave communications are usually combined with massive multiple input, multiple output technology.
Now, I'll talk about how beyond 5G can be a solution to implement smart cities. One major application of Internet of Things includes smart cities. Beyond 5G technology enhances the processing and communication of IoT systems by making them more efficient and faster. Holographic connectivity is a new trend that has been noted in the area of IoT, whereby each and every device is connected to the network. Thanks to the network speed of beyond 5G connectivity, technologies based on holography will enable the integration of various technologies and communication between devices that could not be connected previously. By collaborating IoT systems and beyond 5G technology in smart cities, this leads to the development of diverse architectures with the potential to gather large amount of data. For example, a new concept called Reconfigurable Intelligent Surfaces (RIS), wherein every environmental object is coded with man-made intelligent surfaces of configurable electromagnetic materials may emerge as a result of beyond 5G technology. They are used for indoor windows of buildings located in smart cities. It allows buildings to receive signals without interference, and communication among people is easily facilitated. When it comes to beyond 5G, visible light communication is another sort of technology that cannot be overlooked. VLC is a wireless communication method which allows the transmission of information at a high speed with visible light. The information acquired through this technology is transmitted by modulating the intensity of light from the light source. Integrating VLC in smart cities facilitates vehicle-to-vehicle and vehicle-to-infrastructure communication. While the goal of vehicle-to-vehicle communication is to improve traffic safety via a mesh network whereby vehicles exchange information with each other, vehicle-to-infrastructure communication enables vehicles to communicate with stationary infrastructure components. Since it operates on a large bandwidth at terahertz frequencies, a much higher data rate is expected to be achieved with beyond 5G compared to the current 5G technology.
While implementing 5G and B5G may significantly benefit the enabling of smart parts and smart cities, there are several challenges that has to be tackled. This includes to guarantee high levels of quality of experience, maintaining efficient energy consumption, and building secure network communications. To enable applications for smart cities and guarantee high levels of quality of experience, high data rate with low latency is required. To enable 6G technologies, frequency expansion is required as the data rate requirement is 1 terabyte per second, which is equivalent to 1000 gigabytes per second. Moreover, in order to achieve low end-to-end delay, data packets must be transmitted in smaller frame sizes. However, to achieve reliable transmission, efficient forward error correction schemes are required. These schemes will require long transmission time, and unfortunately, long transmission time is not possible as beyond 5G networks should maintain a latency of less than 1 meter per second. These challenges must be addressed in the physical and network layers. On top of that, the deployment of B5G exponentially increases energy consumption. Every device in B5G or 6G, such as smart devices and applications, will implement sophisticated signal processing mechanisms. Moreover, heavy processing and high energy are required to process big data and for the network nodes of technologies such as AI for enabling smart parts and smart cities. Therefore, high energy consumption becomes an issue. As this increase in energy consumption is inevitable, the issue of harvesting, charging, and conservation of energy must be tackled. End-to-end power consumption optimization must be done, and to date, this remains a challenge. Another challenge that will be faced in the near future as a result of implementing visible light communication is to provide high levels of security. The networks have to protect against many vulnerable points. In the recent years, more attacks have been developed against 6G visible light communication technologies. Such attacks and threats may include authentication attacks, access control attacks, jamming attacks, data modification attacks, and eavesdropping attacks. Given that there are an infinite number of use cases that could occur in the real world, new testing methodologies must be developed to validate the security and performance of visible light communications.
So, that has been our take on what technologies lies beyond 5G, how it will change the network layers, and how it can be implemented in smart cities. We hope that this video has been informative to you. Feel free to leave us a comment if you have any more questions to ask. Thank you for watching.